All right, so here we're going to combine what we learned with continuity with a little of what we learned with intermediate value theorem. So you have your definition of continuity right there. Those same three pieces, she flipped the limit existing and f of c is defined, doesn't matter what order those come in right there, but those three parts for definition of continuity. All right, and these are going to ask just kind of more advanced, I kind of call these AP style questions about continuity to prove whether something is continuous or discontinuous. All right, so use the definition of continuity to prove that the function is discontinuous at the given value of a, sketch the graph of the function. So we have to prove that this is not continuous somewhere. So when you're doing that, you have to show which one of these three rules does this break. Okay, so I'm going to start out with f of c is defined, and right away I'm going to run into a problem here. So I'm going to do f of 3. So that's going to be 3 squared minus 3 minus 6 over 3 minus 3. All right, and that's going to give me 9 minus 3 minus 6. So that's 0, and then that's 0. All right, so we know from doing limit problems that that's a problem. Okay, what happens here is that this factors, so f of x is equal to x minus 3 times x plus 2 over x minus 3. The x minus 3's cancel, and you're left with x plus 2. Okay, so if you were to graph this function, which they asked us to graph it, so let's go ahead and do that. You would just be graphing this linear function. So you have a y-intercept of 2 and then a slope of 1, so up 1 over 1. And then eventually you're going to hit this x equals 3 spot. And if you were to plug in 3, you would get 3 plus 2 is 5. So you get 3, 5. And that's going to be a hole in the graph. Whenever it cancels out like that, you get a hole. All right, so that's what the graph of this function would look like. Okay, so now it's we've proven that we could say here that f of 3 is not defined. So f of x is discontinuous at a equals 3 or x equals 3, whatever. All right, and that does that. It's a point discontinuity, so you would have to redefine this original function. So basically, anytime that your denominator is equal to 0, you're going to fail this rule right here. F of c is not going to be defined. Okay, you don't have to worry about going into limits. Really, the only time the limit's not going to exist is, I guess, with an asymptote, but it would also be f of 3 is not defined. So a lot of these kind of have some overlap, where it could be multiple rules, and it's just kind of whichever rule you figure out first is the one that you're going to go with. All right, next problem. Use the definition of continuity to prove that the function is discontinuous at the given value of a. All right, so when I start looking at this and I start thinking about what could make this not continuous, well, this is a linear function. Linear functions are always continuous. This is a quadratic function. Quadratic functions are always continuous. So the only place these could be discontinuous is if they don't attach to each other at the point 0. Okay, so I see that there's an equal sign here, so I know in my head that f of 0 is going to be defined, but I'm going to go ahead and plug it in and get a value here. I'm plugging it into the top. So f of 0 is equal to negative 2 times 0 plus 2, which is equal to 2. All right, so f of 0 is defined. So the next step would be to figure out, does the limit exist? Okay, so to do that, we're going to do a limit from the left and set it equal to a limit from the right. And if those are equal, then the limit does exist. And if they're not equal, then it doesn't. All right, so the limit as x approaches 0 from the left, we want to do 0 because that's our point of interest in this problem. All right, so from the left would be the top function, negative 2x plus 2. And then that needs to equal the limit as x approaches 0 from the right. And that's going to be the bottom function, x squared plus 1. So if you plug in 0 here, you get 2. If you plug in 0 here, you get 1. So those limits are not equal. Go up here and put not equal. So the limit as x approaches 0 of f of x does not exist. Therefore, f of x is discontinuous at a equals 0. All right, we weren't provided with a graph over here, so let's draw our own. All right, so I'm going to start by plugging in 0 for x, and I get 2. And this is a linear function, so I'm going to go down 2, left 1. That's not going to be right, so don't do that. It's a negative slope, so I'm actually going to go up 2 and left 1. And that'll give me my negative sloping graph going to the left. And then I'm going to plug in 0 down here, and I get positive 1, but it's an open circle because it's not equal to there. And then I'm just going to plug in a couple numbers. So if I plug in 1, I get 2. If I plug in 2 squared is 4, plus 1 is 5. So 2, 5. And this is a parabola, so it's going to go like that. And you can see that it is a jump discontinuity between those. That's why the limit doesn't exist there. All right, use the definition of continuity to find a value of k that will make the function continuous everywhere. So we did a problem similar to this on the continuity day notes. This one's a little bit harder because you have k's in both pieces of this. And so just solving the equation at the end is going to be a little tougher. But the idea behind it is still the same. Okay, so the main thing with piecewise functions is that the limit must exist. So I'm always going to kind of default to doing a left-hand limit and a right-hand limit on these piecewise functions. Okay, so I'm going to do the limit as x approaches 2. Okay, 2 is our point of interest here. It says continuous everywhere, so it did not give us a specific point to look at. But again, think through the problem for a minute before you start. Okay, this right here is a quadratic equation. That is always continuous everywhere. This right here is a linear equation. That's always continuous everywhere. So the only place where these could have a discontinuity is at x equals 2, where they attach to each other. Okay, so if we make sure that that is continuous at that point, then we know we will have a function that's continuous everywhere. Okay, so that's why I'm doing the limit as x approaches 2 from the left. All right, now they try to get tricky on us here, so be careful. The x is less than 2 is on the bottom here. So 8x minus k. Then equals the limit as x approaches 2 from the right of x squared plus kx. So plug in 2 and I get 16 minus k. Plug in 2 and I get 4 plus 2k. All right, I'm going to subtract 4 over here and get 12. I'm going to add k over here and get 3k. And so I end up with k equals 4. All right, just to finish this up, let's rewrite our function with the k plugged in. So this is x squared plus 4x if x is greater than 2. And it's 8x minus 4 if x is less than or equal to 2. And then let's make a graph. All right, so I'm going to start by plugging in 2 on top. So 2 squared is 4. 4 times 4 is 8. So 4 plus 8 is 12. So I'm just going to kind of mark this as 12 right here. Open circle there. Sorry, I messed up. X is greater than 2, so that's going to be an open circle. And then if I plug in 3, 3 squared is 9. 3 times 4 is 12. So 9 plus 12 is 21. So it's going up. I'm not going to plot any more points, but it's a parabola. It's going up like that. Okay. Plug in 2 down here. 16 minus 4 is 12. All right, that's a closed circle. So see how this closed circle is going right on top of this open circle? So it's going to overtake that right there. So that's going to turn it into a closed circle. All right, then I have a slope of 8, and I'm going to the left. So I'm going to go down 8 over 1. So this is 4 right here. I'll do one more. I'm going to go down 8 and over 1. So that's negative 4 right there, and that is the y-intercept. And so there's our line going like this. And we can see we have a continuous function. The limit from the left is approaching the same point as the limit from the right, and they're both approaching a closed circle which satisfies the definition of continuity. All right, that's it for that one. Hope you had fun. See you with the next one.